My name is Anke Arentsen. I'm currently a postdoc at the observatory in Strasbourg, and thank you for listening to my talk on the kinematics of metal poor and very metal poor stars in the Milky Way bulge region. The Milky Way bulge region, or the inner galaxy, is a complex region with many overlapping stellar populations. And the most prominent one can be seen easily in this nice artist impression and is often referred to as the boxy peanut-shaped bulge. And this bulge is thought to have formed from the galactic disk, so an in situ bulge formation. And this is partly supported by the rotational profile seen here in this figure for some data. And it actually has been found that it's rotating like a solid body. So these are signatures that it is an in situ bulge forming from the galactic disk. There has been a question also whether there could be on top of this a classical bulge component, so a spherical, more pressure supported component that did not form from the galactic disk. And observations suggest that there cannot be a very large component, if there is any, because of the velocity dispersion profile. That is actually not high enough to host a massive classical bulge. And secondly, there could be other leftovers still from the galactic disk in this region that are contaminating. And then we have the galactic halo, which actually has its highest density in the very inner regions of the Milky Way, overlapping with the galactic bulge. And there's a range of metallicities present in the galactic bulge region. Here is a metallicity distribution function from a typical survey, the Argos survey, showing that most of the stars have metallicities between solar and -1 or 10% of the solar metallicity. So at low metallicity, metal poor stars, they're not that many, but there is a tail. And now for the very metal poor stars, there are very, very few present in normal bulge surveys. But these stars are very interesting because they are thought to have formed before the more metal-rich stars. So they're the older stars and really trace the ancient components in the inner galaxy. So then how to find more of these stars? How to find the metal poor hay in a metal-rich needle stack that is the galactic bulge. So strategies that have been employed successfully in recent years a lot is using metallicity sensitive photometry or a specific tracer such as RL stars. And in this talk, I will focus on the first, using metallicity sensitive photometry and specifically from the Pristine survey. So here's a color diagram where in this calcium HK magnitude is the metallicity sensitivity. It's a narrow band filter on these two strong calcium lines. And here you can see very nicely how metal poor stars separate from metal rich stars in using just colors of stars. And in this way, we can select a very clean metal poor sample to follow up with spectroscopy. And this is what I've been doing in the Pristine Inner Galaxy Survey, or PIGS. Here on the left-hand side, I'm showing the spectroscopic footprint follow-up with the AAT of metal poor candidates. And so far, we have about 12,000 spectra of metal poor candidates with low resolution and intermediate resolution spectra that are very good for getting stellar parameters and metallicities and good radial velocities, which is important for the kinematics. So as I've shown before, normal bulge surveys here, Apogee and Argos, they typically don't have many stars below metallicities of -1. And then here I'll overplot the results from PIGS. We can see that PIGS starts to peak where the other surveys are going down. So they're really complementary, where PIGS is looking at the very metal poor tail of the inner galaxy. There's actually a few thousand stars, 2,000 stars below -2 and almost more than 6,500 stars below -1. So it's a great sample for work in the metal poor inner galaxy. So one question to ask is how the kinematics in the inner galaxy change as a function of metallicity for stars of different populations. And in Argos, a normal bulge survey, if they split the stars in different metallicity bins, so supersolar, and then here two metallicity bins. And on top is the rotation curve, and on the bottom is the velocity dispersion. And we can see that the velocity dispersion is very increasing if you go to lower and lower metallicity, but the rotation is very similar. until you get to their lowest metallicity bin, which unfortunately doesn't have that many stars. But they start to see a slower rotation and an even higher velocity dispersion. So then here is where PIGS comes in. We can start at their low metallicity end and actually extend this to even lower metallicities. And here for our most metal-rich bin, it agrees quite well with typical bulge surveys in the rotation and the velocity dispersion. But then if you get to the next metallicity bin, we can start seeing a decrease in the rotational velocity and an increase in the dispersion. If we take the next metallicity bin, we can see an even lower rotation, even higher velocity dispersion, and the same for very metal poor stars below -2, where we start losing the signature of the rotation, at least apparently. So this is for all stars in PIGS, assuming that they're in the inner galaxy, but we know that there's a mix of stars that stay within the inner galaxy and stars that are just passing through. So these are halo interlopers. And to be able to look at this, we can estimate the individual distances and orbital properties of the star instead of using just the average radial velocities. So deriving distances is really challenging, and we're fortunate to be able to collaborate with the Starhorse team, Anke Arentsen and Christine Chiappini in Potsdam, using the combination of Gaia parallaxes, PIGS spectroscopic accelerometers, photometry, and a Milky Way prior to get the distances for the PIGS stars. And then we use that together with the Gaia proper motions, the PIGS radial velocities, to integrate that in a potential similar to that of Bertaiatal. And this is work by Giacomo Monari, together with others here in Strasbourg. So overplotting the stars on this barred potential that are in PIGS, we can see they're overlapping very nicely with the very inner region. And in fact, 90% of the stars is within 3.5 kiloparsec of the galactic center. And also within about 2 kiloparsec of the galactic plane. So here I'm showing as a function of metallicity, the fraction of stars that stays confined within the inner galaxy, within 3.5 kiloparsec. And we can see that it's actually decreasing as a function of the metallicity. So for stars at metallicity -1, more than 60% stays within the inner galaxy. But if you get to the extremely metal poor stars, it's only 20% of the stars. So the halo interlopers increase with decreasing metallicities was also something seen last year by Combs, a different metal poor survey with less metal poor stars. Overall, they're less metal poor and the number is also smaller, but they can see the same trend that we can now start to see in higher resolution. So our confined fraction is actually a bit higher than what was seen in Combs, and I don't yet know why. This is all very much still work in progress. And we can then also look at the stars that stay within 5 kiloparsec, which is actually a much larger fraction, and then within 10 kiloparsec, so kind of inner halo. So in this talk, I'll mostly focus on 3.5 and 5 kiloparsec, which are kind of two different selections of inner galaxy stars. So in other metal poor bulge surveys, these halo interlopers, what kind of effect does it have if you remove them? So in Combs, here on the top is again the average velocity and the velocity dispersion on the bottom for not confined stars and for confined stars. And here the rotation looks quite similar, but the velocity dispersion really decreases if you remove the interlopers, which makes sense. And this is something similar seen in Kunder et al. For the Ara-Lyra sample, where here on the right-hand side is the velocity dispersion. It's just higher for halo stars in blue than for the bulge stars. And actually, they're also seeing still rotation for some of the bulge stars here in green. So please listen to their talks on their work as well. So what happens for PIGS if we start making cuts on, for example, the apocenters? Here's again the same plot that I showed you before for all of the stars with all the different orbits. And then the next slide I'll show for only stars that stay within 5 kiloparsec. And I'll flip a few times between them. And you can see very clearly that the velocity dispersion drops. And actually the rotational signature becomes cleaner because you're removing just the outliers from the halo. And you still see this decrease in the rotational velocity. And if you keep only stars within 3.5 kiloparsec, this becomes even more visible. And what's interesting here is that there's still some rotation. There appears still to be some rotation, even in the very metal poor stars below -2, which was not really seen before, but now is visible. So this projection of longitude and using the radial velocities only is very useful, but now we have more information. We can actually use the tangential velocity of the orbit, so the velocity along a circular orbit, and see how that changes as a function of metallicity. So that is shown here in even smaller bands of metallicity, and we can see this decrease in the rotational velocity. And actually I'm plotting it here for different heights above the plane. And the closer you get to the plane, so the red, actually the velocity is higher. And here on the right-hand side is the velocity dispersion. It was a function of metallicity, and it's really increasing if you go to lower metallicity, as we saw before. So then I'll plot the same thing for stars that stay within 5 kiloparsecs. So we're removing really the halo outliers. And we can see on the right-hand side, the velocity dispersion profile is much more flat as a function of metallicity. And on the left-hand side, it's much more clean, this decrease in the rotational velocity. And it's also very clear that there's a difference in height above the plane. So red, yellow, and blue. The closer you get to the plane, the faster the rotation. And it's still visible in the very metal poor range. And then here's the same for within 3.5 kiloparsec. And these again look very similar. So to summarize, what do the kinematics of metal poor stars do in the galactic bulge? If you get to lower and lower metallicity, there's a decrease in the galactic rotation, but it's still visible for very metal poor stars. And secondly, the rotation seems to be higher closer to the plane than further away from the plane. So this is an indication that these stars are not rotating as a solid body, but maybe more like a spheroidal rotation. And secondly, the increase in velocity dispersion, if you get to lower metallicities, is largely due to halo interlopers, stars coming from further away. So then what does this mean for the formation or evolution of galactic bulges? As you go to lower and lower metallicity, it's important to keep in mind we're looking at really the overlap region between bulge and halo, or disk and halo. And it's tricky to really disentangle what components different stars belong to. So if we are seeing this rotational signature as very metal poor stars that are part of a boxy peanut bulge, this tells us something about the presence of very metal poor stars in the early galactic disk in the very inner region. And this is an interesting possibility. And secondly, even if you just have a spheroidal component like a halo or a classical bulge, there can still be a dynamical influence of the bar on the spheroid that can make it rotate and give it the signature that we still see. But also, even if that's not the case, you can still have some net rotation, for example, with a certain accretion event that had a certain angular momentum. So these are all things that can influence the rotational signature, and we're still trying to figure out exactly what it means. And I think what's going to be very helpful for this in the future is more chemistry, more information on the chemical abundances of the stars. And for that, I really look forward to the foremost survey, which will target both our Lyrae in the bulge and very metal poor stars pre-selected from pigs. So it'll be a very interesting time to be able to disentangle more what's happening in the metal poor inner galaxy. Thanks.